Hey guys, whenever we've dealt with a linear equation in one variable so far, whether we've tried to solve it using the balancing method or the transpose method, we've always ended up with one solution, a unique answer, x equals to some specific value. But what if that doesn't happen? What if you don't have a unique solution? In this lesson, that's exactly what we're going to explore by discussing some special cases of linear equations in one variable. But before we move on to linear equations, I want to quickly touch upon two preliminary concepts that will be more and more useful as we go ahead in our mathematics journey.
Note 1.
Reciprocals. The reciprocal or multiplicative inverse of a number is that number which, when multiplied with the number in question, gives back 1. So if your number in question for which you're trying to find its reciprocal is an integer a, then the reciprocal would be 1 upon a. But if the number in question for which you're trying to find a reciprocal is, let's say, a fraction p upon q, then the reciprocal would be q upon p. In both those cases, you can verify that a into 1 upon a equals to 1, as well as p upon q whole multiplied by q upon p equals to 1. Keep this in mind.
Note 2.
Distributive property of multiplication. Let me state this simply first of all. A into left bracket b plus c right bracket equals to a into b plus a into c. So you were able to distribute that b and c to get multiplied with a individually by removing them from the chains of that bracket and bringing them into individual multiplications. Let me give an example to make this clearer and more intuitive. Let's say I give you the question 4 into 7 plus 4 into 13. Now, well, you could of course multiply 4, 7, 4, 13 and add those two products to get your final answer. But what is a quicker way of solving this? If you think about it, 4 into 7 is nothing but saying that I've got 7 4s, and 4 into 13 is nothing but saying that I've got 13 more 4s. So you are adding a group of 7 4s and 13 4s. And it kind of seems like since you have got 4s only, then you have a group of 7 and a group of 13. So in total you've got 20 4s. So 4 into 7 plus 4 into 13 is nothing but 4 into within brackets 7 plus 13 close brackets equals to 4 into 20. That's exactly right. And we can manually verify this logically intuitive result as well. 4 into 7 is 28, 4 into 13 is 52, and 28 plus 52 is 80. Now, 4 into 20, which is what we simplified this to, is also 80. Therefore, the distributive property of multiplication has been verified using this example, and this is a really useful tool throughout arithmetics as well as algebra. Alright, with that in place, we can now move on to the two special cases of linear equations in one variable.
Case 1.
X plus 1 equals to x plus 2. Off the top of my head, I can't really think of a number such that you get the same result if you add 1 to that number and the same result if you add 2 to that number, because the number would stay the same and you're adding two different amounts to it. But I don't know, maybe let's just rely on our methods. So let's start with the transpose method to solve this linear equation. We've got x plus 1 equals to x plus 2. I don't know, let's transpose the x from x plus 2 from the RHS to the LHS. So the LHS would become x plus 1 minus x because positive to negative, and the RHS would become simply 2. So the equation is now x plus 1 minus x equals to 2. Now on the LHS, we can do the x minus x and those would cancel out. So we would just have plus 1 on the LHS, and the RHS is 2. So the equation becomes 1 equals to 2, which is counterintuitive because that is never possible. 1 and 2 are entirely different. So maybe this might be a limitation of the transpose method. So let's try solving the same linear equation using the balancing method. Let's go. X plus 1 equals to x plus 2. Subtracting x from both sides of the equation, we have the equation changing to x plus 1 minus x equals to x plus 2 minus x. So let's perform that subtraction on both sides, and x would cancel out on both sides, and we would be left again with plus 1 equals to plus 2. How can 1 equal to 2? There seems to be a problem. The reason for this is because this linear equation has no solution. Like, you might want to say that the equation is wrong, the question is problematic, there is a mistake, but we mathematicians, being polite people, say not that the question is wrong, but that the equation has no solution. And this is something you will discover more and more, particularly when you jump into quadratic equations and high level mathematics. There will be times when there genuinely is no solution to the question. Let's talk about another example. 4x plus 4 equals to 2 into left bracket 2x plus 1 right bracket. Well, we have got brackets in the right hand side, so we can open those up, which is what I say when I mean multiply 2 with the contents of the brackets through the distributive property of multiplication. So in the RHS, we had 2 into left bracket 2x plus 1 right bracket, which would change to 2 into 2x plus 2 into 1, which would become 4x plus 2. So the RHS is now 4x plus 2 and the LHS remains 4x plus 4. So we are saying 4x plus 4 equals to 4x plus 2. Very similarly to the first example, whether you transpose 4x from one side to the other side and thus cancel them, you would eventually get 4 equals to 2, which is not possible, and thus even this equation has no solution. Let's talk about another equation though. 2x equals to 3x. Can you really think of a number such that if you multiply 2 by it, then it gets the same result as when you multiply 3 by it? 2 into x equals to 3 into x. Surely such a number must not exist, right? And we can even try this using the balancing or transpose method. We can either transpose one of the x to the other side or divide both sides by x, and the x's would cancel out and you would end up with 2 equals to 3, which is impossible. So this equation also has no solution, right? Absolutely wrong. There is a unique solution, and I want you to pause this video and give it a moment of thought. Two x equals to 3x. What is that one possible value of x which could satisfy this equality? The answer is x equals to 0. Why? 2 into 0 would give you 0. 3 into 0 would also give you 0, and thus 0 equals to 0, and thus the equality would be satisfied. This is a really interesting problem that you should not discard. So yes, the first two examples were linear equations without any solution at all, but the third one did have a unique solution. Before cancelling out two variables, consider the possibility of them occupying 0.
Case 2.
2x plus 2 equals to 2 into left bracket x plus 1 right bracket. We do not like brackets because what we're really interested in is the full expression that lies behind the veil of those brackets. So let's break the shackles of these brackets by opening them up, by which I mean, of course, multiplying the 2 that was outside them with the contents x plus 1 within the bracket using the distributive property of multiplication. Thus, the RHS is 2 into left bracket x plus 1 right bracket equals to 2 into x plus 2 into 1 equals to 2x plus 2. But the LHS of the original equation was 2x plus 2 as well. Therefore, the equation becomes 2x plus 2 equals to 2x plus 2. But what does this mean? This means that this linear equation has infinitely many solutions. In other words, if you were to put any real number in place of x, 1, 2, 3, 1.5, 10 upon 6, root 2, any of those real numbers in place of x that you could possibly imagine, this equality would stay satisfied. Another way of proving this in a more abstract but logically rigorous manner is to just do a little bit of linear equation solving. So transposing 2x from the RHS to the LHS and then transposing 2 as well from the RHS to the LHS, we would have this equation changing to 2x plus 2 minus 2x minus 2 equals to 0. And therefore, everything would get cancelled out to give 0 equals to 0, which is of course always true. So no matter what number you were to put in place of x, since there was a 2x to the left and a 2x to the right, and the constant values on the left and right were also the same, this equation would always hold true. Let me give you another example. 3x minus 4 equals to 2 into left bracket x minus 2 right bracket plus x. Now, we don't like brackets, so we get rid of them by applying the distributive property of multiplication on the RHS of this equation. Let's leave aside the plus x for a little bit because it's neither in multiplication nor within the bracket, and let's focus on 2 into left bracket x minus 2 right bracket instead. So that would become 2 into x minus 2 into 2 equals to 2x minus 4. Now bringing back the x, the RHS becomes 2x minus 4 plus x equals to 3x minus 4. Therefore, since the LHS is the same as the RHS, 3x minus 4 equals to 3x minus 4, the expressions are the same. Therefore, the linear equation, through the same logic, can be said to have infinitely many solutions. The solution set of x is the set of all real numbers. Don't let the difference in the initial format of the expressions on both sides fool you. If you just do a little bit of manipulation, then you can see when both of them look and in fact are the exact same. But let's move on to a slightly more intriguing example. 5 upon x equals to 10 upon 2x. So we've got 10 upon 2x on the RHS, but that's a fraction that we can reduce or simplify a little bit because the numerator is 10, which can be thought of as 5 into 2, and the denominator is 2x, which can be thought of as 2 into x. So we've got 2 as a common factor in the numerator and denominator in the RHS. Thus they can be cancelled out so that the RHS changes to 5 upon x, but the LHS of the original equation was 5 upon x as well. Therefore 5 upon x equals to 5 upon x, and this linear equation also can be said to have infinitely many solutions. But can we also say that the solution set of this equation is the set of all real numbers? That if you were to put in any number in place of x, this equality would get satisfied? Or is there some caveat out here? I would appreciate if you would pause the video and give this a second of thought. There is one number which will create an issue. The same number that troubled us in the third example of case 1, that number is 0. Why? Because if you were to put 0 in place of x, that would mean you are saying 5 upon 0 equals to 5 upon 0. But remember what I told you earlier, and a rule that you have probably heard multiple times, you can never divide by 0. Even if you do that division on both sides, it's just not defined.
You have broken the rules and thus you have been kicked out of this mathematics arena.
Just kidding, but what I mean to say is that x equals to 0 cannot be a solution of this equation. Any real number, with the exception of 0, however, is included in the solution set. So yes, 5 upon x equals to 10 upon 2x, which is really just 5 upon x equals to 5 upon x, can have any value occupying x, with the exception of 0. I don't think linear equations in one variable with no solution or with infinitely many solutions are all that common, but I just wanted to alert you of their existence and why they occurred, how they occurred, and what we should make of them. I hope you're comfortable with all of these things, but until next time, comment your doubts below, subscribe for more, share this with your friends, catch you in the next one.